Okay, so we'll do capacitors in this chapter, and we have about 40 minutes, and I'm going to finish the lecture. Okay, so I might go a little fast. So we've talked about capacitors before. So let me start off by showing you a simulation.
This is the last chapter?
I'm sorry?
This is the last chapter, right?
For exam 2, yep. All right, so to make a capacitor, what you need is any two pieces of metal. Okay, so you can take these two pieces of metal, and that's a capacitor. Okay, any two pieces of metal can be a capacitor. Okay. Then if you hook the two pieces of metal to a battery, here's what happens. Okay. Electrons flow from here to the first piece of metal, and these electrons will repel an equal number of electrons from this metal, and they'll go to the positive end of the battery. Okay, so this capacitor is said to be charged. Now this is called a parallel plate capacitor for obvious reasons. If you take two metal plates that are parallel to each other, and they're called parallel plates. The reason we talk about this is because you can give the capacitance of this capacitor in terms of the geometry. Okay, if I wanted to know the capacitance of these two pieces of metal here, I can't give you a formula for that. Okay. So anyway, this is a parallel plate capacitor. Okay. What have we done by charging a capacitor when the capacitor is not, Okay, so what we have done is we have charged this capacitor, and what we did was we transferred energy from the battery and put it here. Okay. And why would we do that? It seems like we just moved energy from one place to another.
So the energy can be used all at once. Energy can be released all at once. So
It can be released very fast. Okay. Yeah. So this device can release its energy very fast. Okay. You can release it as fast as you want, depending on the circuit you hook it up to. Okay. This guy, on the other hand, releases his energy very slowly. Okay. So for instance, now you've charged this capacitor, and this is the circuit of your flash cameras in your flash camera. So you've stored energy in the capacitor, and there you go. You can release that energy very fast. Okay. All right. So that's one of the big uses of capacitors. Okay. So here is a parallel plate capacitor. Okay. Again, the reason we deal with parallel plate capacitors is you can give its capacitance in terms of the geometry of the plates. Okay, so this is the area of a plate, and d is the distance between the plates. Okay. So if you wanted to make a large capacitor, you can try and increase the area of the plate. Okay, so for instance, they make these buses that run on capacitors. Okay. So here's a bus that runs on capacitors. At every stop, it charges itself very fast. Okay. And then to the next stop, it uses the energy stored in the capacitor to run. Okay. And of course, if you are getting electricity from solar panels and windmills, then the operational carbon footprint is zero. And this is a very good thing in big cities and stuff like that. The advantage of capacitors is, we'll talk about supercapacitors. They can last up to 20 years, and they can be charged millions of times. Lithium-ion battery lasts only about 5 years, and it can be charged only 500 cycles. Okay. So we'll talk about uses of capacitors. Okay, again, capacitors are devices that can release their energy very fast. Okay, so here's a parallel plate capacitor. Energy stored in a capacitor is used to light flash bulbs. Okay, so for instance, in these things you can store up to, these are typical numbers, 20 joules. Okay, 20 joules is 20,000 watts. That's 20 kilowatts. And you can release that in 1 millisecond. Okay, 10 to the minus 3. Oops. 10 to the minus 3 kills that. That's 20 joules. Okay. So let's see what this is. 200 into 100 watts. So this, with this 20 joules, you can light 200 100-watt bulbs for a millisecond. So that's what you can do. And that's enough to light, if this room was in complete darkness, you let that flash light up and you can take a picture. You can turn night into day. Okay. So capacitors can store electrical energy just like a battery, except that they can discharge it very, very fast. They're used in tuning receivers. We'll talk about this when we do AC circuits, filters and power supplies, and energy and charge storing devices. Yeah. Okay, you can take any two metal objects, and that's a capacitor. Okay. And when the capacitor is uncharged, there's no energy stored in it. You want to store energy in it, you charge it. How do you charge a capacitor? You just connect it to a battery and you have charged the capacitor. Yeah, that's how you charge it. Okay. And there'll always be equal and opposite charges on the two pieces of metal. Okay. If this has a charge of minus 10 coulomb, this will have a charge of plus 10 coulombs. Yeah. Now what this says is plates or the metal objects are conductors. They are equipotential surfaces. Okay. So, and if the battery is a 10-volt battery, the potential difference between these two guys is 10 volts. Okay. So everywhere on this, let's say the voltage, the potential is minus 5 volts. Everywhere on this, it'll be plus 5 volts. Okay. So the capacitance of a device like this is defined as how much charge can it hold per volt. The larger the capacitance, more charge it can hold per volt. Okay, so that's what that is. This is coulomb and that's volts. Coulombs per volt is called a farad, after Mr. Farad. Okay. Here are electrical symbols for various devices. That's the electrical symbol for a wire. There's the symbol for a capacitor. This is the symbol for a resistor. This is the symbol for something called an inductor. We'll study about these guys in about 3-4 chapters. And what these guys do is they don't like changes in currents. So if you try and change the current through them, they'll fight that change. This is just a switch. This is a current measuring device. This is a voltage measuring device, a current measuring device. That's a battery, and this is an AC source. You saw this circuit just a minute ago. So when you close this switch, charge flows from here, it charges this capacitor. So you have transferred energy from here to there. Then you can open the switch, and here you have a store of energy. And when you're ready to use it, close the switch. And this energy will discharge through that. This could be a flash bulb, and you take a picture. This could be somebody's heart fibrillating, and the defibrillator is just a capacitor, and you discharge that through their chest cavity. Okay. And hopefully restore a regular heartbeat. Or, if you get to play with big toys, this could be charging a laser, and the lasers are shooting at a pellet, and you're making fusion reaction. Okay. So you can do all kinds of fun stuff. Okay, so here's a parallel plate capacitor, two metal plates parallel to each other, and their capacitance can be given in terms of the geometry. Epsilon naught is permittivity of free space, it's a constant. A is the area of the plate, and D is the distance between them. Okay, so that capacitor that you saw, the supercapacitor that's used in a bus, okay, we'll talk about how you can make a very large capacitor. Okay, so to make a large capacitor, what is it that you can do? Okay, so you can have very large parallel plates, but you got to fit them in a bus, so we'll show you how to increase the area of the plates. You can also try and decrease the distance between the plates. Okay.
Do the plates have to be like one-dimensionally flat, or can they
Yeah, no, so. There. Here's a metal sheet, an insulator, metal sheet, and then you can wrap it up and put it in your pocket. All right, so for parallel plates, here's the capacitance in terms of the geometry. You have cylindrical capacitors, there's a conductor. Again, for a capacitor, what do you have to have? You have to have two conductors, okay? And here is an inner conductor and an outer conductor. And the capacitance of this guy, so a coaxial cable has capacitance associated with it, okay, is for a cable that long is L times 2 times the Coulomb's constant log of B, that's the inner radius, times A, okay, log of B over A. Okay. And that's the electric field in this region when it's charged. You can have two concentric spherical surfaces, okay, and the capacitance is given by that. A is the area of the inner conductor, and B is the area of the outer conductor. Now, here is what you can do. You can make this guy go to infinity, B go to infinity, and this term reduces to that. B going to infinity is like not having this. So you can use a spherical object, a single object, and charge it, okay? And that can also behave like a capacitor. So you guys might have seen a Van de Graaff generator, and you charge it, and there's a capacitance associated with it. What happens if you have two capacitors? If two capacitors are connected like so, these guys are said to be connected in parallel. And their equivalent value is just the sum of these capacitances. Okay, so if you have a bunch of capacitors and you want to make a larger capacitor, you just connect them in parallel, and the capacitance you have is just the sum of those capacitors, yeah?
Why wasn't we connect them in series?
What's that?
What if we connect the
we're getting there. Okay. So when you want a larger capacitor, you connect them in parallel. So if you want to store more and more energy, you connect a whole bunch in parallel. If you connect them in series, this is a series connection. Okay. So here is what happens. Okay, let's see. Electrons flow from here to there. Let's say 10 electrons came here. They'll repel 10 electrons, which will go there. These will repel 10 electrons. Okay, so when you connect them in series, the charge on each one of them is the same. When you connect them in parallel, this capacitor, if this is a 10-volt battery, this will charge to 10 volts. This also is seeing 10 volts. That'll also charge to 10 volts. So when you connect them in parallel, they all charge to the same voltage. When you connect them in series, they all get the same charge. Okay? The equivalent capacitance is 1 over C1 or 1 over C2, 1 over C3. Okay, so look at this. 1 over C1 is a positive number, here's another positive number, here's another positive number. So this number is bigger than any one of them. So that means this equivalent value is smaller than any one of them. So if you connect a bunch of capacitors in series, what you get is a smaller capacitor than the smallest one. Okay. I'm sorry? No, so let's say you wanted 3 microfarads in some circuit, and all you had are 5 and 10 and something like that. So you can connect them in series and make a smaller capacitor. Okay. It's a political joke, so if you want less for your money, then you give your money to the government. And I'm not anti-government, I'm just joking, all right? All right, oftentimes you'll have a bank of capacitors, and then you'll want to find the equivalent value. Okay, so you might connect something like this in a circuit, and the reason you would do that is this guy has one job, this guy has another job, and so on. Okay, so you might want to see the voltage across this guy in some case, and so on. All right, so when you analyze the circuit, you will need to convert that to a single capacitor. Okay, so here's what you do. See, these two guys are in parallel, so the net is just the sum of these two. That's 40. That's 4. These two guys are in parallel, so you reduce it one step at a time. So 6 plus 2 is 8. Now these two guys are in series, and the way you add series is, capacitors is 1 over 8 plus 1 over 8 equal to 1 over 4. Okay. So these two guys connected in series is 4 units. These two guys connected in series is 2 units. And now these two guys are in parallel, and that's 6 units. Okay. So that's how you do it, one step at a time. You have a mess of capacitors, and you can reduce it to a single capacitance. All right, so when you charge a capacitor, we said that you've stored energy in it. How do you say you've stored energy in it? What do the positive and the negative plates want to do? They want to attract each other. So if you're holding them apart, it's like you've stretched a spring. And a stretched spring has energy. Okay? So whenever you charge them, okay, the more charge you put on a given capacitor, it's like you made a stronger spring. Okay, so you stored energy in the capacitor. This is how much energy you stored. the capacitor. Okay, if you want to store more and more energy, so for instance, for that bus, you want to give that bus a longer and longer range, you'd want to store more and more energy. Okay, so think about this one. So to store more and more energy, you can make the capacitor big. And I'll show you how to make the capacitor larger. Or, what else can you do?
Decrease the distance between plates.
Well, that'll increase the capacitance. Charge it to a higher voltage. What limits you charging to higher and higher voltage?
The fact that you can't hold them apart at a certain.
To the point where energy is discharged via lightning.
There you go. Okay, very good. All right. So those are the two limiting things. Okay? It's very easy to charge it if there was no lightning discharge. We could charge it to higher and higher voltage. Okay, so those are the limiting things. Okay. Now, when you charge these guys, there's an electric field between the plates. Okay. And so what this slide shows you is the following. The capacitance is 1/2 CV square. That's the voltage. The voltage is the electric field strength times the distance between the plate. There's the capacitance in terms of the area for a parallel plate. Okay. So this is very important. Make sure you understand this. Okay. And then we'll rearrange all of that. There's A, there's D, one of the D cancels. There is area times D. What is this fella? That's the area of the plate times the distance between the plate. That's the volume between the plates. Okay? And times this. What is this guy? What is this E?
Energy stored.
What is that E? We just said that the voltage is electric field times distance. That's the electric field. Okay, what was this? Oh, this should not be C, that should be U. Okay, I'll fix that. That's energy. So this is energy. Energy is volume times energy density. So what this is saying is, anytime you create an electric field, the energy stored per unit volume is that. The energy stored in terms of the electric field is given by that. Okay. So what you've learned is, anytime you create energy, you've stored energy. Okay. So for instance, you can smear this wall evenly with positive charge. You smear this wall evenly with negative charges. You just saw that there's energy stored. We can think of that energy stored in terms of the electric field created in this room. Okay. So similarly, in a later chapter, you learn you can store energy in magnetic fields as well. So anytime you create electric and magnetic fields, you have stored energy. Okay. So this is the energy stored in electric fields per unit volume. Okay, of course you charge these two plates, they want to get together, so to prevent them from getting together, what do? You place an insulator between them. This is called a dielectric, okay? So it will prevent the two plates from coming together. There's other things that this guy will do. This guy also allows you to charge them to higher voltage because of two things. What is the electric field that happens in air? What field do you need for lightning to happen in air?
3 times 10 to the 6.
Very good. 3 million volts per meter. Okay? So let's say we put plastic. Do you guys know what this is? This is lightning in plastic. What's that?
Ink green, you know where you, isn't it where you throw electrons in like a block of acrylic and you hit it with a hammer? It creates that?
No, this is lightning to this plastic. To create lightning in this piece of plastic, you need 30 million volts per meter, 10 times the greater.
So you're saying that if you put something between them that's not air,
Mhm.
has a higher, higher threshold than air, then you could technically charge it higher than it would.
There you go, my friend. I'm very close to buying you a soda, but I don't think I'm going to buy one. All right. So you guys understand? All right. So that's called the dielectric strength of a material. Okay. See, there is the dielectric strength of air. So these are various materials. Polystyrene, 8 times greater. Okay. So you could charge that capacitor 8 times to 8 times greater voltage. Okay.
A vacuum doesn't have a dielectric strength?
It's 1. Oh, yeah, no. Yeah. Well, there's nothing to ionize.
Yeah.
Okay. So the dielectric strength of perfect vacuum is infinite. Okay. So dielectrics are insulators. They provide increased capacitance, increased maximum operating voltage, and mechanical support. Okay. What they do is, so that's why you put dielectrics in between. What dielectrics do is their molecules either polarize or they have permanent dipole moments, and if you put them in between there, they will line up, and the more these dipoles line up, the greater the dielectric constant, the greater by which the capacitance will increase. Okay, so if you put a dielectric in between, the capacitance increases by the dielectric constant. Okay, it increases by this factor. All right, when they do that, see, this becomes a positive layer, these two cancel each other, these two cancel each other, this becomes a negative layer, and there's an induced field in the opposite direction. So it weakens the field against when it was just air was there. And that's why you can charge them to a higher voltage. Okay? So dielectric provide increased capacitance, increased maximum operating voltage, mechanical support. Okay. So you can see that Teflon, the dielectric strength is 20 times greater. Okay. So you put Teflon between those two parallel plates. Now you can charge it to 20 times greater voltage. Okay, so this is lightning in plexiglass. So here are types of capacitors. This is, you can make them with metal foils. These are metal plates in oil. So the dielectric is the oil there. Silicone oil, the dielectric constant is 2.5 and the dielectric strength is 5 times greater. Yeah. All right. I don't know how many of these keyboards still use these capacitors, but so in your computers, if you hit a certain key, how does the computer know which key you hit?
Nowadays they use like lasers,
Hmm?
so they shoot lasers between them and like send the signal. But
Okay.
these ones, you would.
So here's how these work. So each of these keys are connected to a 5-volt battery. Well, I guess so 5 volts. Now when you press this key down, this distance decreases. The capacitance, when D decreases, the capacitance increases. And the capacitance is also Q over V. Since the voltage is the same, if the capacitance increases, more charge flows in. So you hit a key, charge flows into that key. And that's how you know which key you hit. Yep. All right, so this is a big boy toy. Z machine, okay, is a controlled nuclear fusion reactor at Sandia National Lab, New Mexico. Okay. So the idea is the following: you take a small pellet of tritium and stuff like that. You shoot it simultaneously with a whole bunch of lasers. Dump a whole bunch of energy and heat it up. That's the temperature you'll heat up the little pellet to. Okay, anybody remember the temperature at the center of the sun? Astrophysicist?
15.6.
All right, 15 million Kelvin. Okay. You heat your little pellet to 1,000,000,000 degree Kelvin. Almost 500 times hotter than that. Okay, and some of those nuclei will fuse. Why do you have to make it hotter than the sun? Because this has lower density and the sun, at the center of the sun, it has a lot of density, and so there are enough molecules to hit together and fuse. Okay? Look at this. The power output of the Z machine is about 100 times the combined power output of all power plants on Earth. Okay, when they fire that, okay, so the Z machine uses a bank of capacitors connected in parallel to store 1,000,000 joules of energy. Now, 1,000,000 joules of energy is not a whole lot. With 1,000,000 joules, here's what you can do. So let's say my weight is not 100 kg, but we'll say it's 100 kg times acceleration due to gravity is 10 meters per second square. That's 1,000 and 1,000 meters. So if I jump from a kilometer, when I hit the ground, I have 1,000,000 joules of energy. Okay? That's the amount of energy. Okay, this energy is discharged through a target about 1 cc. 1 cc is that much. Okay. In a nanosecond, a billionth of a second. So you saw that you need a capacitor to do that. So you have a whole bunch of capacitors. All these lasers are firing at the same time for a billionth of a second. So for that billionth of a second, the power rating, which is power is energy divided by time. So for a billionth of a second, the power of this machine, the power discharge in that machine, is greater than all the power plants on Earth. Yeah.
What do they use it
For fusion. Yep. So they're fusing material, fusing stuff. They got more energy out of it than they put in the lasers 2-3 years ago.
So something would go wrong really.
What?
Like if something went wrong, it could go really wrong. Or not.
No. 1,000,000 joules is nothing. You pay 12 cents for 4,000,000 joules of electricity. One unit of electricity is 3.6 into 10 to the 6 joules, and your electricity bill is billed on that, and that costs you 12 cents.
But when the lasers are on specifically, still no, would you say?
You'll be safe.
Okay.
So remember we said we want to build supercapacitors. Supercapacitors are large capacitors. Okay, back in the day, we will use capacitors, and in our lab we'll use microfarad and nanofarad capacitors. a billionth of a farad. 20 years ago, maybe 30 years ago, 1 farad capacitor was a large capacitor. These days they can make a 5,000 farad capacitor. You can go to Google, you go to Amazon and you can buy it for $100. Okay, so for a capacitor, okay, you want to make a large capacitor, you can increase the area tremendously. You can try and increase the area, okay? And that's what they do. See, this is, they take powdered charcoal, and then you can charge them. The effective area is the area of all, surface area of all the particles. Okay? So 2 layers of activated charcoal are given opposite charges and separated by an insulating layer. Okay? And you can make large capacitance. The problem is you can only charge them to 2 to 3 volts, but that's fine. Okay? You can still store 10,000 joules of energy. And that's good enough for these guys. Okay? And you can do all kinds of, and more and larger populations, fraction of the population is living in big cities. And so if you have public transport that doesn't pollute, that's a good thing.